Hello, this is Dr. Michael Hassan, the engineering doctor, and this is lecture number 15. The title of this lecture is Encoders for the course Digital Logic Design for Chapter 4, Digital Design with Standard Modules. The next slide is a disclaimer for you to read. I cite 3 references here, but there are many more references for digital logic design courses. And the chapter 4 contents, we talked about decoders, decoder expansion, design with decoders, code converters, and today we'll talk about encoders. What is an encoder? An encoder is a combinational logic module with basically n input lines and log to the base 2 n output lines. The input lines represent units or devices which may request service, such as, for example, terminals in a time-sharing system or devices and an interrupt-driven microcomputer system. So encoder is extremely useful and has many applications. The outputs represent a unique binary code for each input signal applied to the encoder. As such, it is the opposite of a decoder. The encoder is with either mutually exclusive inputs or a priority encoder. We'd like to see what's the difference between mutually exclusive input encoder and a priority encoder. If the encoder has mutually exclusive inputs, then only one input may be active at any particular instant of time. That is, only one unit can request a service at a time. However, a priority encoder, on the other hand, allows more than one input to be active at a time, of the output code represents the input with the higher priority. So in the priority encoder, more devices can request service, can be active at the same time, but only the one with the highest priority will be recognized, and all the other devices will be ignored. For instance, in priority encoder, when two input lines II and ij such that I greater than j request service at the same time, line II has priority over line ij. So the encoder produces a binary output indicating that the input line with the highest priority. So that is, the line with the highest priority will be recognized, or II will be recognized, and ij will be ignored. We'd like to look at the design of 4-to-2 priority encoder. If we understand really one design, we should be able to go to a higher order like 8-to-3 or 16-to-4 priority encoder. So the priority encoder with 4-to-2 has 4 input lines, I0, I1, I2, and I3. I3 will have the higher priority than I2, I2 higher priority than I1, and I1 higher than I0. So if all the devices recognize service, only I3 will be recognized. The output code which represent the input or the device to be recognized is A0 and A1. A1 is the most significant bit and A0 is the least significant bit. So if you look at the truth table for the encoder, we will have the inputs I3, I2, I1, and I0, and the outputs, which is A1, A2, and G. G, what's G? G actually is a signal which is called a valid output indicator. So G is a valid output indicator, indicates whether any requests are present. From the truth table, we can derive the corresponding K-maps, find the logic equations for the outputs A1, A0, and G. So this is the truth table. Let's understand the truth table. So if if all of the inputs are zeros, all the inputs are zeros, A1, A2, A1, A0, I do apologize, A1, A0, and G will be zeros. Now, once actually I0 will recognize a service, so it's 1, so the output will be 0, 0, which is indicate we are acknowledging I0. This is the code for I0, and G, which is 1, to indicate there is an active and valid output indicator. So G will be 1. Once I1 will become 1, requesting a service, whether I0 is requesting a service or not, we will find that a 0, 1 will be the output of the encoder, which is equivalent to 1, representing device I1. And the I, deliberately I use I to indicate an input interrupting device. So once we have I2 is 1, the output will be 1, 0, regardless on I0 and I1. See, they don't care. Now, if I3, which is the device with the highest priority, I3 is this input, is 1, where I2, I1, and I0, all of them don't care whether zeros or ones, the output will be 1, 1, and B will be 1. So if we do go to K-maps and we simplify for K-maps, we find I1, A1 will be I2 or I3, I0 will be I3 or I1 and I2 prime, and G will be I0 or I1 or I2 or I3. It is very useful to use a 4-variable K-map. You can leave them from the table. It's very useful to use 4-variable K-map and simplify. Once we have, so if we take I2 and I3 to the gate, we take A1, and we take I1, I2 prime, so we need an inverter for I2 prime, I2, so we get I2 prime, then we ended I1, I2 prime, then we order to I3, so we'll get 0 and G for the gate with I1, I0, I1, I2, and I3, and this will give me G. And by this, we have fully designed a 4-to-2 priority encoder. You see the design is very simple, and we can expand this design to a higher priority encoder, as I said, like 8 to 3 or 16 encoder higher than that. So this is the design of 4-to-1 priority encoder, which is extremely important design. And we'll go to the next slide. There are standard encoders actually in the market, modular chips that you can buy. And namely, I named 2 of them, 74147 and 78. Or you could find them 7LS147, 7LS148, where the technology is low power Schottky transistor, which is TTL chips, of course. The 147, the 10 to 4 priority encoder, which is available as an MSI, which is medium scale integration package. In this encoder, the inputs and the outputs are given in complemented form. So if you'd like to use it, look it up actually. I'm sure if you have access to a data sheet, you can have the pin configuration of this chip. However, the 74148 is an 8 to 3 priority encoder with complemented inputs and outputs. The circuit has an output G, which is a valid request indicator or output indicator, and it is also equipped with daisy chain. This is very important for the expansion. So if you'd like to expand the 8 to 3 to 16 to 4 or higher order, so you can do that to expand the encoder by using multiple chips of 8 to 3 priority encoding, which is a 148. So equip daisy chain such that the encoder has an enable input and enable output. Those enable lines are active low. The first encoder must be grounded, taken to ground, and if an extension is needed, the second encoder is enabled. First encoder enable output as shown in the diagram which is coming to the slide. The output enable of that encoder is inactive to terminate the chain. If any input line of an encoder is active, if active, the output enable of that encoder will be inactive to terminate the chain, so you don't allow the error. And this will give the priority to the higher chip, With the connection shown in the next slide, we can handle 16 input, such as the highest priority to I15 and the lowest to I0. We can add more encoders to handle more request inputs needed. So you can see with the connection, we can handle 16 inputs. From I0, those are active low, so they are active when they are zeros. And the outputs correspondingly will be complemented. Okay. So we have these outputs. So this will allow us to, as you see, the enable input has to be grounded for this to be active. But if any of those are active, any input from I8, I15 is active, this enable output will be high, and this chip will be inactive. So this will give you a priority. This input, which is I15, will have the highest priority. But if any of those are inactive, the E output will be enabled, and the highest priority will be I7, and this is I7 0. And you will have two GS for the upper chip and the lower chip, which is the output, valid output indicator. So, and those outputs, which is output 0, output 1, output 2, they are inverted, works, and can represent the code from here. So if this one is active, the output here, if this is active, which is active 0, the output definitely will be equivalent to the code 0. So what you will get 0, 0, 0, okay? Otherwise, you will get 1, 1, 1, 1 if they were not inverted. Since they are inverted, so you'll get 0, 0. If none of those active and this is active, the output here will be 0, 0, 0. And those will be high, of course, be high. And GS will be 0 to indicate that this is a valid output. So 74LS148 is a very good chip used in microcomputer technology to acknowledge interrupting devices for interrupted-driven microcomputers, and is a very useful chip. This is the end of lecture 15, which is encoders, and I'd like to thank you so much for listening to this lecture. Please subscribe, and I will hopefully see you soon in the next lecture. Sincerely, Dr. Hassan.